Hey Dominic, how you doing?
Good, how are you?
Good. I'll dispense with the camera tonight just so that I won't have to turn it off in the middle.
Yeah, sure. Sorry
Okay.
I'm a little late.
That's
The
okay.
I have to book a room at the library to be able to have a place and had to kick someone out, so
Oh, okay.
it's all right. Um, okay. So the most recent things are trigonomic or trigonometric, I guess, integrals. And
Something like this.
yeah,
Okay.
and then the other thing is trigonometric substitution.
Okay. It's real important to cover this first because
Okay.
trig substitution will make so much more sense to you if
Yeah.
we learn how to solve integrals of this type here. Okay. You no doubt in your book have been given a set of rules to consider when solving this.
Yep.
And that set of rules is that if one is odd, pull out, well, let's see. I know how to do it. I'm not sure what the set of rules are, but let's do one. Notice that if I did this integral, I can just use the power rule, right? In other words, this is an integral that we would normally solve by substitution, and where we're looking for f of g of x times g prime of x. Well, that's exactly what we have there. The f of g of x is this, and the g of x is sine x, so the derivative of that is cosine x. So we're looking at that format, which you want to be on the lookout for when you're looking to use substitution. Okay, so we can do this quite easily. It's sine fifth of x divided by 5. And I could go through the substitution if you like, where u would be sine x.
Okay. No, that's okay. I
Okay.
see how that would.
Okay, so now let's consider a more complicated situation where sine has an odd power on it. Well, what I want to do here is I want to take one of those cosines out. So I'm going to turn this into sine fourth x cosine squared x cosine x.
Right. Yeah.
And then I want to take this and use the trig identity 1 minus sine squared x to rewrite it as sine fourth x 1 minus sine squared x, and I still got that cosine x over there. Why do I have this cosine x lying around? Because that's the derivative of the inside, so that I can use the power rule. Well, now we fully distribute.
Okay.
And from here, it's fairly simple. Since we have the derivative there that's going to go with each of these terms, then the answer is going to be sine fifth x over 5 minus sine seventh x over 7. Okay, so when we had an even and an odd, we pull out 1 power of the odd,
Right.
and it doesn't matter whether it's the sine or the cosine. In other words, if we go back and look at the problem where let's make this cosine of fourth, sine of third, let me just switch them around here for a moment. In other words, if the cosine is even and the sine is odd, then what do I want to pull out?
Sine.
Right, and leaving behind sine squared times cosine fourth times sine, change the sine squared into cosines, and repeat like I did on that one. Okay? So if you have one odd and one even, that's what you do. Now
so what happened to that last cosine there?
On the problem we were doing?
Yeah.
Okay, what we had was the integral sine to the fourth x minus sine to the sixth x times cosine. Remember, we had taken a cosine out.
Right.
This turns into sine fourth x cosine x dx minus sine sixth x cosine x dx. So the cosine acts as the derivative of the inside in both cases. So I can use the power rule just with that and this.
What do you mean by the power rule?
Okay.
I know how that works.
Now let's not call it the power rule then. Let's call it substitution. Because some schools will go ahead and call this the power rule when in effect they really don't mean that. Let's figure out how to solve this with substitution. U is equal to what?
Cosine x?
No, it would be what's inside. What's inside this thing is sine x. It's sine x that's being multiplied 4 times. So I'm going to let u equal sine x. But the key is du is now equal to cosine x dx, which means dx is equal to du over cosine x. So now when I rewrite this integral as an integral of u, well, u to the fourth instead of sine x to the fourth. I still got this cosine x momentarily. And in place of dx, I'm going to put du divided by cosine x. Now I have an integral, the integral of u to the fourth du, which is equal to u to the fifth over 5. Now go back and substitute sine. So we have sine to the fifth over 5 minus sine to the seventh over 7. What happens is that if you do substitution enough, you learn to look for this situation where you can kind of use, I suppose it shouldn't be called using the power rule, but it really is. What we're looking at here is f of g of x, a composite function, that is a composite function, times g prime of x. Why is sine to the fourth x a composite function? Because g of x is equal to sine of x, and f of x is equal to x to the fourth. So f of g of x would represent this composite function, sine to the fourth of x. And then the derivative of g of x is cosine x. So whenever we see this situation here, know that this derivative is going to show up in the denominator when we use substitution, and I don't even need to go through the substitution process to know that the integral of this is going to be the integral of that. If I just apply the power rule to this term, it'll all work out.
Yep.
So whenever I recognize that I have a f of g of x composite times g prime of x, I can use the power rule. In other words, another example of that would be let me put the x behind here. I'm going to put the x over here. In fact, let's make it 2x. So if I were to be asked to integrate this, well, I recognize that this is a composite function. That's the f of g of x part. And this is the derivative of the g of x part, the g of x being the inside. So this, again, I recognize as f of g of x times g prime of x, and I can just apply the power rule to x squared plus 1 to the 1/2, turning it into x squared plus 1 to the 3/2 multiplied by 2/3. In other words, it's not necessary for me to go through the u substitution, even though that's what I'm really doing. If I was going to explain it to somebody that didn't understand it, I would go through the u substitution to convince them that you're always going to find this 2x in the denominator and it'll cancel out. If you were to have gone through the u substitution. Okay, so let's consider a different trig combination here. That was when we had, one of them was odd. What if we have just even? And no cosine, we'll say. Even though we could have an even cosine also. But the rule is if the powers of both are even, then use this following technique. And I could say that there's a cosine there to the 0th power if I wanted to. In other words, if I wanted to be clear about the rule, I'll just write the cosine in with like that. Okay? That's the same thing as not having a cosine. So I don't need the cosine to apply this. So what I'm going to use is the power reduction rule from trig. So instead of integrating, I don't know how to integrate sine squared of x because there's no cosine next to it. If I had a cosine next to it, it'd be easy. But without the cosine, I don't have any way to find an antiderivative of that, except if I use the power reduction.
So I got to be careful to not just take the antiderivative of that sine squared x, just based on that rule that...
Just the power rule?
Yeah.
If you did, this is what you'd get.
Yeah.
But now take the derivative of this, and you will not get that.
Yeah.
Because in order to take the derivative of this, you have to take the derivative of the outside, which is sine squared x, but then you have to multiply it by the derivative of the inside, which is cosine x. So that's why it's not easy to find an antiderivative for sine squared of x. So we convert it to cosine of 2x. Okay? So this is going to turn into the integral of 1/2 dx plus 1/2 times the integral of cosine of 2x dx. Okay, now the integral of 1/2 dx is x over 2 plus the integral of cosine of 2x is sine, negative sine rather, of 2x divided by 2. Notice that if I take the derivative of negative excuse me, the integral of this is positive. That's not a negative sign. Wrong sign. In other words, to take the integral of cosine of 2x, I can use the power rule. It's the sine of 2x divided by 2. Notice that if I took the derivative of this, I would get cosine of 2x. So it's easy to take the integral of the cosine of a constant multiplied by x. And it's also easy to take the integral of the sine of 16x. That's just negative cosine of 16x divided by 16.
Yeah.
So it's easy to do that, not easy to do that. So whenever we have sine squared, or in a worst case scenario, let's look at sine to the fourth, how we would do that, we have to break this up into two of these.
Right.
In other words, it's this thing squared. But that's not really a problem. Notice that if we go ahead and square that thing, we get well, the first term is going to be 1/2 squared, so that's 1/4. Second term is going to be twice 1/2 times cosine of 2x over 2. Well, that's cosine of 2x. And the last term is going to be cosine of 2x over 2 squared, which is cosine squared of 2x over 4. Okay, we know how to integrate that. We know how to integrate that. Don't know how to integrate that yet. But since we can use the reduction formula again, in other words, let's just focus on the tough one. Let's take the 4 outside like that. Okay, so the reduction formula for cosine squared of 2x is 1 minus cosine of 2x, which in this case is 4x, because it's 2 times 2x, all over 2.
That's the reduction formula?
Yeah, here let's look at the reduction formulas. The two important ones are this one, which is 1 plus cosine of 2x over 2, and this one, which is 1 minus cosine of 2x over 2. So what would cosine squared of 2x be?
2 minus cosine of 4x.
Well, cosine squared of 2x, let's use a substitution just to make it easier to see. Cosine squared of u, well, that's clearly going to be 1 minus cosine of 2u over 2. But what is u? U is 2x. So if I put a 2x in there, it's really 4x. So that's how I get this, almost. In other words, cosine squared of 2x is 1 minus cosine of 2 times 2x, or the cosine of 4x, all over 2. So now when I'm trying to integrate that thing, I'm going to integrate this instead, because once again, that's easy to integrate, to find the antiderivative of that.
Why couldn't you just Well, could you just write the cosine squared as the 1 minus sine squared? Or would that not get you anywhere?
It doesn't get you anywhere, because then it leaves you with the problem of integrating the integral of sine squared of 2x. In other words, that's not any easier to do than this was.
Okay.
We still have to use the reduction formula, only we use that one up there. The key is the cosine squared of 2x, when you use the reduction formula, is coming up with that 4x. Or if I was doing the cosine squared of 3x, it would be 1 minus the cosine of 6x all over 2. Okay, so basically what we've learned how to do is all combinations of sine and cosine. Whether n and m are both even. If they're both even, I'm just going to use the Pythagorean identity and turn it all into one or the other. If one of them is odd, I'm going to pull one of those out and use the power rule, what I call the power rule. And if they're both even, we're going to use the reduction. So I can now handle all cases of sine combined with cosine. It would be laborious if you gave me something like well, in this case, I can choose the cosine to pull out or the sine. It doesn't really matter. And then convert the other into the other. In other words, if I pull out a cosine here,
yeah,
now I'm going to convert that completely into sine. It'd be 1 minus sine 8th of x. And then I'll be able to operate on the whole thing easily. So we can do any combination of sine and cosine. Have you learned tangent and secant yet?
I guess sort of, but it's just going to be the same.
Similar concept, only a little different. In other words, let's take an example where we have 3 and 3. They're both odd. I want to pull out a tan secant because the derivative of secant is tan secant. So instead of having a cosine sitting out here on the side like we were with sine and cosine, I want whatever the derivative of that's going to be. So I'm going to turn this into tan squared x secant squared x times tan x secant x. This will act as my derivative of the inside when I finally get this into nothing but secant. Okay, well, how do I do that? Well, tan squared of x is equal to secant squared minus 1 times secant squared times this thing. See where we're going here? This is going to be secant fourth x times tan x secant x plus or minus secant squared x times tan x secant x. Now I can use the power rule on that because that's the derivative of the inside. So the answer is going to be secant fifth x over 5 minus secant third x over 3.
Where did that tan x secant x come from?
I pulled it out. I pulled one of each out. Notice that I reduced the tangent from 3 to 2, and I reduced the secant from 3 to 2 when I went to this step here.
Oh, yeah, okay.
Then I converted the tan squared into secant squared minus 1. And I still had this down here.
Okay, yeah, I see.
Then I just separated stuff and distributed that. And then once I get to this step here, that's when the integral, finding the integral of this is easy, because tan secant is the derivative of the inside, which is secant. If I had, instead of odd, the other situation would be where I'm going to turn it all into tangent. Well, the derivative of tangent, let's make this odd even. Let's make it like that. I guess I could do the same thing that I just did. I could pull out a tan secant, turn the remaining tan squared into secant squared minus 1, and do it the way I just did it. But I can also do this a different way. In other words, sometimes you have to pull out, you're going to have to turn it all into tan, and the derivative of tan is secant squared. So if I'm going to do the problem that way, then I want to pull out a secant squared. In other words, I've got this, and I'm going to pull out a secant squared to have handy to be able to turn, that will be the derivative of this after I turn it all into tangent. Well, here I'm going to replace secant squared with tangent squared plus 1. The first secant squared I'm going to replace with tangent squared plus 1. And I'm going to leave this secant squared over here because I'm going to use the power rule on that, and I need the derivative of the inside, which is tan, to be sitting here. So the answer on this is going to be tan to the 5th over 5 plus tan, that would be 6th over 6 plus, when I integrate tan cubed, I'm going to get tan 4th over 4. So there's my answer. And the difference is that I had to pull out a secant squared, or I want one secant squared that I can pull out if I'm going to turn the rest of it into tan.
Mm-hmm.
If I'm going to turn the rest of it into secant squared, then I want to pull out a tan secant. Okay, between those rules, between sine and cosine and tan and secant, that covers just about every kind of trig function.
Mm-hmm.
So it turns out that no matter how hard of a trig function I put up here, we can integrate it using that techniques that we just learned. So trig substitution works on the following concept. I have no idea how to integrate that polynomial. It's too difficult. It doesn't match any of my rules. Substitution isn't going to work. Parts isn't going to work. But what if I could turn this polynomial into trig functions?
Right.
Then I can integrate it and then turn it back into a polynomial. So that's why trig substitution is such a powerful technique for integration, is it allows you to handle all kinds of very difficult problems. Let me get some examples and I can explain better. There's something very, very important that you have to accept when you're doing integration by trig substitution. Let's look at this problem here. Okay, first note that none of our basic integration rules apply here. Notice that the derivative of the inside, if I were to let u equal 9 minus x squared, is 2x. Well, what are we going to do with that? We got nothing to do with that now. So u substitution isn't going to work.
Mm-hmm.
However, if I recognize this as one of three formats that I'm looking for, the formats that I'm looking for are...
I have them here too.
Yeah, if the integral is of the form a squared minus u squared, then I'm going to let u equal a sine of theta.
Mm-hmm.
That's just something you want to memorize. If the format of the integral involved is a squared plus u squared, then I'm going to let u equal a tan of theta. And finally, if the format involved is u squared minus a squared, the opposite of the first one, then I'm going to let u equal a secant of theta. Okay?
Mm-hmm.
At this point, I would suggest to you that you not try to understand why, that you just memorize these rules. It will become apparent at some point when you do some of these why this works.
Yep.
Okay? So let's apply the rule to this problem here. Since we have the format is this one, a squared minus u squared, right? What's a and what's u equal to?
A is equal to 3, and u is equal to 3 sine theta.
Actually, u is x. In other words, if we're looking for this format here, we have a squared minus x squared. So 3 squared minus x squared is our a squared minus u squared.
Oh, yeah, sorry.
Okay? Okay, so now we're told to let u equal a sine of theta. Okay, so I'm going to let x equal 3 sine of theta. Well, our goal is to substitute everything we see up here. I want to substitute for the dx, I want to substitute for the x squared, and I want to substitute for the square root of 9 minus x squared. Well, x squared, let's substitute for, let's find dx first of all. Dx is what?
Negative 3 cosine x.
Just 3 cosine.
Oh, yeah, sorry, I'm thinking.
Okay, everybody gets confused. Between differentiation and integration, it's hard to keep those signs.
Yeah.
It really is. Okay, so dx is 3 cosine theta d theta, right?
Yep.
Okay, so we've solved for that. That's what we're going to substitute for that.
Mm-hmm.
What about x squared? What does x squared equal to? Next thing we want to substitute for is that. If x is equal to 3 sine theta, x squared is equal to 9 sine squared theta.
Yeah.
Okay? Now, notice what happens. I'm going to write it small here. Well, dx is 3 cosine theta d theta. X squared is 9 sine squared theta. And inside, we've got 9 minus 9 sine squared theta. Okay, so now our entire integral of the polynomial has become an integral of a trig function. So let's try to solve this. Well, this actually solves pretty nicely. Well, the square root of 9, if I factor out a 9 here, I leave behind 1 minus sine squared theta. Well, that's cosine squared theta. Right?
Mm-hmm.
What's the square root of 9 cosine squared theta?
3 sine theta.
Right. So now I can replace this with 3 cosine squared, 3 cosine theta. It was 9 times cosine squared theta.
Mm-hmm.
So the square root of that's that. That cancels with that, and I'm left with the integral of cosecant squared theta, 1/9 d theta. Okay, we're not done yet.
Right.
The key here is when we let u equal a sine of theta, what kind of triangle were we describing? We were describing a right triangle where if this was theta, and we're saying the sine theta is u over a, right?
Right.
So this has to be u, this has to be a. Well, guess what this is? A squared plus u squared.
Mm-hmm.
So what is the integral of cosecant squared of theta is negative cotan of theta.
Right.
Okay, so what we have here is minus 1/9 cotan of theta.
Is it cotan squared?
No, it's just cotan. In the same way that the integral of tan is equal to secant squared,
Right. Right.
the integral of cotan is negative cosecant squared.
Mm-hmm.
So, I'm sorry, the derivative is what I meant. Now I'm the one getting them mixed up. That's all you need in a tutor, to get differentiation and integration mixed up. Okay, so this becomes our answer, but notice we don't want an answer as a trig function. We started out with a polynomial. We want another polynomial as our answer. Well, the reference triangle we used was this. So what is the cotan of theta?
Adjacent over.
It's the reciprocal of the tangent.
So it's adjacent over opposite?
Yeah, so it's a over u.
Yeah.
Well, a is 3, and u is x. Plus c.
Yeah.
So the concept here is we turn our polynomial into nothing but trig. We can integrate the trig because it's actually easier to integrate trig functions than it is to integrate polynomials. And then once we get an answer as a trig function, we look at the triangle that we were using based on the fact that we let u equal to a sine of theta. Now, notice that if we are dealing with a different format than a squared minus u squared, we wouldn't let u equal to a sine of theta. We would let u equal to, what were the other choices? A tan of theta or a secant of theta. And each of those constructs a different triangle but one that you can figure out all three dimensions. Okay? So once you're able to dimension this triangle fully, now you can convert any trig function answer back into a polynomial by just reading it from the triangle. What is the cotan of theta? It's it's a divided by u. 3 divided by x. Integration by trig substitution is really, really tough. The only thing I can really suggest to you is that you memorize what I have right here on the right. If you memorize those three rules and those three conditions, it will get you through. You won't really have to understand what you're doing, you just have to do it. And that's the best thing I can tell you, because after you do a bunch of them, understanding will come. Let's do another one.
I have a quick question here.
Okay.
If the number inside the root sign there isn't a square number, like it's like x squared minus 7, do you just use a equals root 7?
Yes.
And then
or a equals, if it was the square root of 9 minus x, then a is 3, u is square root of x, in order to make it a squared minus u squared. Okay, I can integrate that, so I would never be doing that. But let's do one more example. What format do we have here? Which one of these three?
Is it this a secant theta?
No. Is it the top, the middle, or the bottom? In other words, when we have a squared minus u squared, we're going to let u equal a sine theta. When we have square root of a squared plus u squared, which looks pretty familiar,
oh, yeah.
We're going to let u equal a tan of theta.
Yeah.
So that's our first step. Let's let u equal a tan of theta. What's a?
1.
And what's u?
Is it, let's see, is it just x or is it?
2x.
2x, yeah.
Because then this would be u squared. So what we have is a squared plus u squared. Okay, and before we go further, let's go ahead and draw the triangle that they're talking about. By letting u equal a tan of theta, we've decided the triangle we're going to deal with. If u equals a tan of theta, then tan of theta is u over a, so this has to be u, this has to be a. I did it wrong on the last problem, didn't I?
What, your a and u?
Did I let x equal a sine of theta? I guess I did. I guess I did it right. Okay. Yeah. No, I think when I drew my triangle, I drew it like this instead of putting the a there. That's where the a belonged. For this first case scenario, if you're letting u equal a sine theta, that means sine theta is u over a. So I would have dimensioned it this way. I did the first one wrong. I was reading the answer out of the book. I got the right answer. Oh, no, I didn't get the right answer. Yeah, I had the triangle dimensioned wrong.
Oh.
I had the a down here, which would have been correct for u equal a tan of theta, but it wasn't correct for u equal a sine theta. In other words, for this one, the a has to be here. Now, this is a squared plus u squared. Notice that the third side, when we draw the representative triangle, the third side is always what we're looking for in the integral. This becomes the format that we're looking at. That's why we're going to let u equal a tan of theta whenever we see the square root of a squared plus u squared, because we can handle this now. Okay, so this is our representative triangle, but let's proceed. Remember, we have to substitute for everything we see in this integral, so we need a dx. So what's my next step?
To set x equal to
Let's take the derivative of this, so we'll end up with our dx. In other words, du is going to be 2 dx, so dx is going to equal du over 2.
yeah.
Hold on, I'm all screwed up here. Completely lost what I was doing. Okay, if u equals a tan of theta, then 2x equals 1 tan of theta. So x is tan of theta over 2. Is that better? You must have been wondering, what the heck was I doing? Let me erase the rest of this stuff. And I understand trig substitution. That's how hard it is. Well, I understand it and I still can't get it right.
Yeah.
Okay. So let's see. We're doing this integral. So first of all, we need to find dx d theta. Dx is going to be secant squared of theta over 2 d theta. So now I know what to substitute for dx, this. Okay, well, the square root of 4x squared plus 1, well, let's find out what x squared is. X squared is equal to what? Based on x being equal to that.
1/4 tan squared theta.
So now let's substitute. As always, when I'm tutoring these, I never have enough room. Okay, so for dx, I'm going to substitute secant squared theta d theta. And for the bottom, which was square root of 4x squared, well, this is x squared, so I'll plus 1. That's my new integral to do. Nothing but trig function.
Yay.
Okay, the 4's cancel. I've got the square root of tan squared theta plus 1, which is secant squared.
Right, okay.
So now I've got the integral of secant squared over secant, or just the integral of secant d theta. Okay, well, the integral of secant d theta, which is another one that's hard to memorize, but we know what it is. It's 1/2. No, we had the 1/2 out front. How did I miss my 1/2? Ah, because I didn't put the 2 in. When I substituted for dx, I wrote secant squared theta d theta. There's this 2 also. So there was a 1/2 out here. So the integral becomes 1/2, and then the integral of secant theta is natural log of secant theta plus tan theta plus c. So there's my integral as trig function. Now I got to convert it back to a polynomial. Well, if I look at my original picture, I need to figure out what secant theta is and tangent theta. So if I look at this picture right here, only a is 1, and u is 2x. So this is 4x squared plus 1. So there's my reference triangle that I'm using for this problem. So what is secant of theta equal to?
1/2 x. X over 2.
Well, secant is the reciprocal of cosine. Cosine would be 1 over this hypotenuse, so secant would be this hypotenuse over 1.
Yeah.
So the secant theta is the square root of 4x squared plus 1. So I'm going to substitute that for the square root of 4x squared plus 1. Nothing said that this answer had to be pretty. And then I need the tan of theta. Well, reading from that same triangle, what's the tan of theta?
It's 2x.
Right. So plus 2x. So there is my answer to the original problem in polynomial form. And I had absolutely no way of doing this by any method other than trig substitution. Trying to solve that as a polynomial, I don't know how to do it. I don't know if there's a way or not, but I know how to do it using trig substitution.
Are you allowed to do the substitution in the numerator?
Yes, you are.
Okay.
Let's look at one that has a variable in the numerator. It would be the square root of x squared minus 3. This was one you were talking about. If I wanted to integrate this, and if I want to go from square root of 3 to 2, okay, so on the right, which form are we looking at, dealing with?
The third one.
Okay, so we're going to start this problem off by letting u equal a secant of theta. We're going to draw our reference triangle because we're going to need it later. After we've solved the thing, we're going to need this to convert back to polynomial. So how can I dimension this? So secant theta is equal to u over a. Secant's the reciprocal of cosine, so this must be u, this must be a. Okay? And in terms of x and a, what is u in terms of x? U is equal to x, and a is equal to what?
Root 3.
Square root of 3, right. So now, rewriting this in terms of x and square roots of 3, I have x equals square root of 3 secant theta. Let's go ahead and replace in this model here. This is square root of 3. This is x, which makes this the unknown side that you figure out is always the thing we're dealing with.
Mm-hmm.
Notice we were having to deal with x, the square root of x squared minus 3. That turns out to be that third side. Okay, so now I need to substitute for this, I need to substitute for this, and I need to substitute for that. Let's find dx first.
So, yeah.
Remember, the derivative of secant is secant tangent.
Yeah.
So there's dx. X we have, that's right there. So what is the square root of x squared minus 3? Well, the square root in terms of trig, x squared minus 3 is going to be equal to the square root. If I do it the hard way, it's going to be the square root of this squared, which is 3 secant squared, minus 3. And notice these always work nicely. That's the beauty of trig substitution, is you always can factor out of 3, convert it to tangent, take the square root of it.
Yep.
So this is equal to 3, the square root of 3 times secant squared theta minus 1, which is the same as tangent squared theta. So now we got 3 tangent squared theta is that. So now I want to substitute everything that I know. So instead of writing it as a polynomial, I'm going to write it as a trig function from square root of 3 to 2. Dx is square root of 3 secant theta tan theta d theta. Square root of 3 secant theta tan theta d theta. That's substituting for the dx rather. What else did I have in my numerator? I had square root of x squared minus 3 equals this, which is multiplied by the square root of 3 tan theta. You with me?
Yep.
Okay, all divided by x, and x was equal to square root of 3 secant theta. So now I have the whole thing, converted, no more polynomials. That's important. When you get done, you don't want a dx, you don't want an x anywhere. You want d theta and thetas everywhere.
Do you need to change your limits of integration?
We can either change the limits of integration when we do this integral, or we can wait until we substitute back in a polynomial for it.
Okay.
No, we can't. We do have to change the limits of integration. We can't do it the other way.
Oh.
Because yes, we can. We can do it the other way. We'll do it the original way.
Yeah, substitution you did before.
Yeah, we can do it. I mean, we could change the limits of integration based on the fact that it's in theta now, but better yet, let's integrate this thing, convert it back to x, and then use these limits of integration. Although this particular problem actually had to do with limits of integration. But we don't have much time here, so let's just do this the easy way. Cancel that, cancel that, cancel that with that, and we end up with the integral of the square root of 3, which I'll take out of tan squared theta d theta.
Mm-hmm.
Well, that's not a particular easy one to do. We have to use the trig substitution, turn that into square root of 3 integral of secant squared theta minus 1 instead of tan squared theta d theta. And this equals, well, the integral of secant squared is tan theta. The derivative of tan theta is secant squared theta minus theta. Evaluated, I could either have changed my limits of integration to evaluate it, or let's now not evaluate this, but turn it back into polynomials and evaluate it at the old one. So what's the tan of theta equal to from my triangle? Opposite over adjacent would be square root of x squared minus 3 over square root of 3.
Mm-hmm.
So what was that again? Square root of x squared minus 3 over square root of 3. There's the tan of theta. What's theta? Theta is is the inverse cosine of square root of 3 over x. Theta is the inverse cosine of square root of 3 over x. Right? In other words, looking at that triangle. This triangle right here. If I ask you what theta was, well, since the cosine of theta is the square root of 3 over x, then theta is the inverse cosine of square root of 3 over x.
Mm-hmm.
So I substitute that for theta. Now I can evaluate it at the original limits, square root of 3 to 2. Even though this is a trig function, it's not really. Not for our purposes here. I can actually evaluate this as a number. I have converted it back to polynomials now, despite the fact that there's an inverse cosine in there. I can evaluate, if I plug in 2, I'm going to get an angle. Okay, well there's a reason this is an example where it is. I'm not going to do this. I do have to change my limits of integration. What was x equal to?
I think it was root x squared minus 3.
Yeah, so now let me go back up here. X is square root of 3 secant theta. X is square root of 3 secant theta. So if we plug in X for 2, we can figure out what the new limit should be in terms of theta. And it turns out to be pi. X is equal to 2 when theta is equal to pi. X is equal to square root of 3 when theta is equal to 5 pi over 6. So we would go ahead and, if we had a definite integral like this, we could go ahead and evaluate it at the new limits of integration and just come up with an answer, a number, instead of giving the answer as a polynomial. In other words, since it was a definite integral that requested a number back, there's no need to convert this back to the polynomial and give it as an answer. We can evaluate it directly as a trig function as long as we change the limits of integration.
Yep.
Okay. We call it a session.
Okay.
Hopefully that's helped. The only thing I can really suggest to you is memorize these 3 things on the right and just use them religiously and work through it, just trying to solve for every piece of this so you can substitute for it.
Okay.
Okay? And that works.
How long do you think it'll be before this is online?
I'll set processing it now. I should be able to put it up by 9 o'clock tonight.
Sounds good.
Okay?
Okay.
All right, Dominic. Talk to you later.
Very
Good luck
much.
on your quiz, your
Yeah,
test,
thanks.
your final, whatever.
Yeah.
All right. Bye-bye.
Later.